Hi everyone.
Okay, so next we have Akanksha, who is going to tell us about semi-numerical simulations of the epoch of helium reionization.
Hi everyone, and thanks to the organizers for giving me this opportunity. So I'll be talking on semi-numerical simulations of the epoch of helium reionization, and this I'm doing in collaboration with Keith. So this is the outline of my talk, and this work is right now under progress. First, I'll just describe what is helium reionization, what goes into modeling helium reionization, and the ionization and the thermal history during the epoch. So what is helium reionization is so already we know what is the cosmic dawn. When the first sources they were formed, they ionized the hydrogen. So early star-forming galaxies could only ionize hydrogen, and the first electron of helium was ionized because they have relatively lower ionization energies. And in order for the second electron of helium to get ionized, we need more energetic photons. So that had to wait until a later epoch at a redshift of between 4 to 3. So this epoch, when the second electron of helium was ionized, is referred to as the epoch of helium reionization. And so when helium reionization happens, then the impact on the IgM is that it will ionize, and also it will introduce, and due to photoheating, there will be photoheating in the IgM. So this impacts the Lyman alpha helium-2 and the H1 Lyman alpha forest lines, and one can get an indirect. Indication that helium reionization happened, but just by looking at these Lyman alpha forest lines. So why it is important to study helium reionization is because it will impact the spatial variations of the high redshift UV background during this epoch, and it also determines the thermal fluctuations of this intermediate redshift IgM. So in order to model helium reionization, so the three main things we need is that first we need the sources, which, as I already mentioned, is largely quasars. Then how they are ionizing, and their thermal impact on the IgM. Previous studies have mostly focused on in-body simulations, hydrodynamics, or some Monte Carlo methods, or analytical or semi-analytical techniques. But these methods are slower, and our goal is that if we can make efficient helium reionization simulation, which can enable parameter estimation studies. So first, modeling of sources. So how do we model sources? What we do in order to model quasars as sources is that first we will have halos from an in-body simulation, which is gadget 4. We use gadget 4. And then we do something that is known as abundance matching, where we assign a luminosity corresponding to that to a given halo mass. But since all halos will not host a quasar, only a fraction of those halos would host a quasar. So that fraction is what is called as, what I'm calling as F1. Here TQ is the quasar lifetime, that is the time over which a quasar has been active. And this is the Hubble time scale. So using for luminosity function, we use the empirical measurements from Kulkarni et al. 2019. And using this, we can assign luminosities to halos. Now, how do we select our halos? So we basically just loop over all the halos in our n-body simulation, and choose a random number between 0 and 1. And if that random number is less than F1, then we say that, okay, that halo hosts a quasar. So for our study, we have, since most of the measurements, they indicate that helium reionization ends somewhere around redshift of 3, we have chosen to work with quasar magnitudes which are brighter than -21. This roughly corresponds to a halo masses of around 2.5 to the power 10 to the power 11 solar masses. For now, we have fixed, since quasar lifetimes are highly uncertain, we have used a luminosity independent fixed quasar lifetime of 40 mega years. So once we have modeled our sources from halos, next is how we model the ionization history. So in order to model the ionization history, we use this script, which is a seminumerical code for reionization with photon conservation, which was originally developed for hydrogen in order to resolve, to make resolution independent large scale ionization maps. And it also resolved the problem of photon conservation, photon non-conservation in excursion set models, which was originally used for hydrogen reionization. So for script, it takes a dark matter overdensity field and an ionizing photon field as an input. And then in every grid cell, it counts the number of photons. So if the number of photons is greater than the number of neutral species, in that case, hydrogen in the original script, then we say that the cell is fully ionized. And then the excess photons are distributed in increasing order of distance. And if we include recombinations, then similarly, the neutral number will increase by the number of recombinations. And if the number of ionizing photons is less than the neutral species, then we just assign an ionization fraction of Ni by N. So what we did, we modified script for helium. So now our neutral species is helium. And in order to get this rate of the number of photons in a given grid cell, this is not working. No, there's no light. Yeah, so in order to get the number of photons, first we need what is the rate of photon emission from each quasar. And that we will have the quasar ACD, which is modeled from Luzo et al., where alpha is taken to be 1.7. And we take our time, this delta T, over quasar. So this delta T is that the time interval between two redshift intervals, and we have taken our redshift intervals corresponding to the quasar bursts. So the total ionizing photon field is given by this, and this NIN. And then we include helium. This is the overdensity. So we will get the overdensity field from our gadget snapshot, and then we can get the neutral helium atoms. We include inhomogeneous recombination by using this rate of recombination integrated over all the previous redshifts. So here we have one free parameter, that is the clumping factor, that accounts for the excessive clumping in regions where there are more number of helium-3 and ions. Alpha is the recombination coefficient, which decreases with temperature. So with this, this is our ionization history. So this black dot is what we are calling as our fiducial model, which will be clearer later on. For higher clumping factors, ionization would be delayed, as is seen here. And these blue lines are for lower clumping factors. So if the clumping factor is lower, then ionization is faster. So we have tested our results, and they converge with respect to time and spatial resolution. So after we have introduced ionization, now next thermal history. So for thermal history, we use this analytical prescription where temperature will change due to expansion of the universe, the structure formation, and if there are other processes. In our case, the other dominant process is just photoheating. Structure formation, these two terms, one is the adiabatic expansion of the universe, and this is where high density regions, they are growing as a result of adiabatic compression or expansion. So using this equation and introducing photoheating due to helium, this is the full evolution due to photoheating due to helium. So we will have one term that comes from hydrogen, which is already in equilibrium, which is ionized and in equilibrium with its background. So we are in a regime where hydrogen and the first electron of helium is fully ionized. And there are two other terms. One is from regions where helium-2 has already been ionized. It is similar to this hydrogen term. And another term where when reionization is happening in the cell, at that time, so the moment there is this dx is changing, there's an increase in temperature. So this corresponds to neutral regions of the cell when they get ionized. So we took TRE. So this TRE is the temperature increase per photoionization of helium. And in this case, this is for hydrogen. For hydrogen, we took the constraints from Methi and Barun and Tirthankar Roy Choudhury's previous paper. And for TRE-HE, this is a free parameter. So it is known that the temperature and density settle to a tight power law, where this T0 is the temperature at the mean density, and this delta is the over density. So, but so far what has happened is that we have not included baryons. So in order to introduce, but when we are talking of thermal history, then we have to introduce baryons somewhere. So in order to do that, since I have less time, so in order to do that, we take a subgrid implementation where we take in every main grid, having some density delta, we assign that delta as the mean density and a standard deviation which is equal to the standard deviation in density at the gene, smooth at the gene scale. Then we map these densities using the fitting formula by Moe and White, and then map them back after evolving them linearly. So this way, this smoothing at the gene scale introduces what baryons would do to dark matter. So for subgrid ionization, we just increase the, we assign all these subgrid density elements an ionization of 0 or 1, such that the main grid DQ, the change in ionization, is implemented. And in between the snapshots, we also introduce recombinations in the similar way we were introducing earlier. So with this, what is expected is that, so this is a scatter plot between temperature and over density. And this color bar shows the density of points. So initially, this line corresponds to neutral helium. So when, I mean helium-2, so as more and more ionization happens, the temperature will increase. And this would, and there are also two other processes. So the overall expansion of the universe would cause a decrease in temperature, and higher density regions would increase in temperature while lower density would decrease. So, so there would be a change in slope. This is again stop working. So there will be a change in slope, and this would manifest to an evolution. I'll stop here after this slide. So there will be an evolution in temperature versus redshift. And these are my two free parameters, clumping and TRE. So, so like I said previously, clumping would delay helium reionization, an increase in clumping, and this TRE would lead to an increase in temperature because now there is more ionization per helium atom. So, so this black line, these yellow points are what has been measured from by Gaikwad et al. From quasar data, and these black lines are my best fit fiducial models. So we conclude that TRE is of the order of 1 × 10⁴ Kelvin, and clumping is about 7.73. Thank you.
Some quick questions.
Does it work? Thanks for the nice talk. Very quick question. Do you also consider the impact of gamma, capital gamma, because that will influence the way your T0 and small gamma work across redshift? And can you constrain that? Also, of course, there are observational constraints. So
yeah. So finally, we would go on to modeling tau effective, and then from tau effective, we can treat gamma as a free parameter and probably put constraints.
But it's not in yet.
No, in this gamma, so by default there are photons in this, so there's no gamma separately, but there's this n dot which would be related to gamma.
Thanks.
Okay, so let's thank Akanksha.